Hey, welcome to what will be probably the last of the videos for the AP curriculum, chronologically speaking. We may do a few more non-AP curriculum topics like nuclear chemistry and organic chemistry, but for the AP curriculum, this will probably be the last one. And what we're going to talk about today are the two remaining quantitative expressions that relate delta G to units that we've discussed. So we're going to be talking about this idea of available or Gibbs free energy. We already did thermochemistry, so we've kind of taken care of that. So today we're going to be talking about how it relates to electrochemistry and how it relates to equilibrium. And we're going to do that quantitatively. We'll work through an example of each, and that kind of provides a nice sort of cap to a lot of the topics in the course, because a lot of things end up interweaving themselves into this final topic. So Gibbs free energy, available energy, relating to topics as far back as thermochem, which we covered early in the year, and then to equilibrium, which was a big focus of the third quarter, and then electrochem unit that we just covered. So again, we might refer to this as Willard's law. No one else does, as far as I know, but this is a relationship between delta G and volts, which is this idea of the electromotive force or electric potential, which we label with capital E, which of course unfortunately is also the symbol for energy, but here we're talking about electric potential in volts. And that mathematical relationship is actually quite easy. It's simply that delta G equals negative N, and again, back in the old days, this was the symbol for the capital F, Faraday's constant, and then E. These days now they just label it with a boring capital F, which is kind of a shame. As I mentioned in class, it took me years to work on writing that F without having to stare at a sample to copy it. So each term in here, of course, has a relationship that we should understand. So delta G being available energy or Gibbs free energy. And by the way, available energy, we're talking usually in kilojoules, but sometimes in joules per mole of reaction. N represents the moles of electrons per mole of reaction. And what that means is, in an electrochemical reaction, how many electrons are being exchanged, how many electrons are being passed back and forth in this reaction. And we'll look at an example or two and talk about that. The fancy script F, Faraday's constant, 96,500 or 485 coulombs per mole of electrons. And if you're kind of looking ahead already, the moles of electrons will divide out, and we'll currently have coulombs per moles of reaction, but we don't want coulombs per moles of reaction, we want joules or kilojoules. Well, the nice thing is that E being measured in volts, the electric potential, because we're measuring that in volts, as it turns out 1 coulomb times 1 volt equals 1 joule. In fact, the units are kind of, the coulomb and the volt were sort of arranged in that way that we have this nice mathematical relationship. So that's going to make life a lot easier for us. So delta G equals negative NFE should, if you look at the equation just very broadly and quickly, we've talked about this already, if I have a positive voltage, so if E is positive, F is also positive, N is also positive. They're all numbers that are like positive quantities, a positive voltage, a positive amount of charge per mole of electrons, a positive number of electrons exchanged in moles of reaction, but then there's a negative at the front of that expression. So that's going to mean a negative delta G. So a positive voltage correlates with a negative delta G. So a working battery has available energy. Handwriting seems exceedingly poor today. So a working battery has available energy, and obviously a non-working battery does not. As a battery loses that ability to work and its voltage drops, as V approaches E, the value in volts approaches 0, delta G will approach 0. So a battery hits equilibrium when the volts are dead, and we get delta G being 0 at that point. All right, so let's look at a sample problem. Let's say that we have the reaction of silver ions floating around in some sort of working battery system with aluminum, where the silver is reduced, it gains electrons and turns into solid silver. The aluminum is oxidized, turns into its most common oxidized state of 3+. That voltage at standard conditions is 2.46 volts. And so if you were asked what is delta G, And we could certainly say, what is delta G standard, that little degree symbol indicating standard conditions, because we have a standard voltage here, 25 Celsius, 1 molar for everything, all that good stuff. Well, delta G would equal negative N. Well, how many moles of electrons are exchanged here? Each aluminum loses 3 electrons. Each silver takes 1, but there are 3 of them, so 3 total. Well, it's not 6, it's the same 3 electrons. These 3 electrons that are gained and lost are the same 3, so we have 3 electrons being gained and lost. So we have 3 moles of electrons per mole of reaction. And then we have our value of 96,500 coulomb per mole of electrons. And then we were given that the voltage is 2.46 volts. So if we look at this, moles of electrons will divide out, and then a coulomb times a volt equals a joule. So if I try to do the math here, somewhat estimating this, I would say probably in the neighborhood of negative 720,000 joules per mole of reaction. If you're doing this at home with a calculator, you'll probably get a better answer than I will, but hopefully I'm somewhere within range. So around 720 kilojoules per mole of reaction. So a battery producing a fair amount of energy that's consistent with a pretty large voltage for an electrochemical cell without modifying it in some way. And so that seems like a pretty reasonable value. Fairly easy calculations to do for these kinds of problems. They're usually not of undue difficulty for Willard's law. So let's move on to Gibbs Law, or Gibbs's Law, depending on how you pronounce it. I'm not really sure. Oops, it's a poor start on my part. So this is the confusion. So is it Gibbs Law or is it Gibbs's Law? Depending on whether you pronounce it, I think, is the determination of whether to add the apostrophe S for a name like this. So Gibbs's Law relates delta G to the equilibrium constant, KEQ. So we have our last relationship here. And again, remember that we said that as reactions favor the products, so K greater than 1, we're going to get a negative delta G. Delta G will be indicating that there's available energy for a reaction that moves to the products. In other words, the reaction that moves to the products does so without needing excess energy. That would indicate that it is favorable for it to do so, and there must, whether usable or not, be available energy. Certainly it's usable when we look at things like batteries, but sometimes it's less usable for a lot of these types of reactions. This expression, when we quantify it, is delta G equals negative RT ln K. So the natural log rearing its beautiful head here. R, rather oddly, as we'll talk about, is the ideal gas law, ideal gas constant. And we'll talk about why that's the case here maybe in just a moment. But delta G, still available energy, still in joules or kilojoules per mole of reaction. And in fact, in this case, we're going to use joules and not kilojoules because of the way the math sort of works out, as we'll learn based on the value of R. So this is kind of weird to see R in here, the ideal gas constant. But remember, the concept of the kinetic molecular theory is simply that particles in motion have all sorts of behaviors. And pretty much all these things we're talking about particles in motion. Remember that we don't really have equilibrium dealing with things like solids, at least not in total. We have to have things that are aqueous or gases, so that there are going to be particles moving around. And whenever there are, there's some fundamental relationships about particle motion as a function of temperature, which T is going to help us with. Because of this, we're going to use the 8.314 version of things, and normally we might associate that with the liters and kilopascals in the numerator, but a liter times a kilopascal, and if you can always hit me up outside of the video here since we're not really live communicating, that's an easy proof to do. So 1 liter times 1 kilopascal is actually a joule. So this is 8.314 joules over moles times Kelvin. And so that's where joules are going to get introduced. Again, it's just sort of an energy of motion of particles. T, of course, is just the Kelvin temp. And K, of course, is our equilibrium constant. And again, the relationship here is that when we have K greater than 1, we get a negative delta G. So a reaction that favors the products produces available energy in some form or fashion. So if we look at a sample problem like this, let's say that our sample problem is a familiar one, the reaction involving the synthesis of ammonia, which Fritz Haber helped figure out. The Haber process, as we know, is sort of the industrial application of how to make this work. And this is a little callback to the topic from earlier. Delta H, if you use heats of formation, delta H for this reaction at standard conditions is negative 92 kilojoules per mole of reaction. And you might be able to predict that delta S is negative. And the reason it's negative, of course, is there are 4 moles of gas particles here. So we have 4 moles of gases on the left and just 2 moles of gases on the right. So we've lost gases, which means we've lost disorder. So the reaction is more ordered or less disordered. So it's actually a negative value for delta S, which we probably could have predicted. Negative 199 joules per mole reaction Kelvin. And what we've got in there then is one of the 2 driving forces. So delta H is exothermic, indicating that this reaction does produce heat energy, but because it creates order, it's not necessarily inherently favorable at all temperatures. There is a temperature at which it flips from being not favorable to favorable. And those would be the kind of things that Haber was able to figure out in industrializing the Haber process. So if you apply these, and we'll sort of skip ahead, but if you use what we call Josiah's law, the delta H minus T delta S formula, delta G under these conditions ends up being about negative 33 kilojoules per mole reaction. And once we have delta G, it's actually pretty easy to find K. K might be a value that is very large or very small and thus kind of hard to come up with a value for. And so that's sort of a tricky thing. So if we start plugging these kinds of numbers into the equation, we can theoretically find this. Now you'll note that delta G is negative under these conditions. And because it's negative, a negative value would certainly indicate that you've got a favorable reaction and thus a K value larger than 1. That seems to be a little bit odd given that the Haber process, was sort of a revolutionary thing, but we also have to remember that ammonia isn't necessarily a gas at 25 degrees Celsius, and so trying to work that into the equation under standard conditions is a little trickier, and so that's something to consider. Okay, so we have to convert this to kilojoules to make, to joules, to make it work, so let's say 33,000 joules. So if we plug in negative 33,000, joules for delta G equals negative 8.314 joules per mole Kelvin times 298, if we keep it under standard conditions, times natural log of K. That would mean the natural log of K is those numbers divided by each other. 24, 33 divided by 24, probably around, I did this earlier, I think it's around 13. The negatives divide out, and then you get a value there of around 13, I believe. And so K would equal E to the 13. And I think when you do that, I did it earlier again, so it's not like I'm able to do exponential functions in my head, but it's around 6 times 10 to the 5th. So certainly a reaction that very much favors the products, which is indicative, again, of a reaction that favors the products in correlation with a negative delta G. So those are just a couple of examples of how to use these other 2 equations that quantitatively relate Gibbs or available energy to other topics, in this case electrochem, which I think is quite simple, and to this equilibrium constant kind of expression. Again, most of the time we use this last one, Gibbs's law, because finding K is difficult for whatever reason. Either the reaction very heavily favors the products or very heavily favors the reactants, and determining K experimentally is very difficult because molarities are not calculable when they're super, super high or super, super low. And so it's an easier thing to work around it using other data like thermochemical data in this case, or electrochemical data if you have that from another case. All right, it's been a pleasure making these videos for the AP curriculum. Hopefully we will virtually see each other soon, and we can talk more about organic topics and nuclear topics. All right, have yourselves a wonderful day.